All right. So our next speaker is Noah Vowell from Michigan State. Take it away.
Thanks, Josh. Hello, I'm Noah. I'm a grad student at Michigan State and a pre-doc fellow at SAO. And I'm excited to show you guys some of the results that we have from trying to use transiting brown dwarfs in order to better understand the planetary mass limit. So you might say that it's just 13 Jupiter masses. This has been solved, and I should pick a new thesis. It's a little late for that, but I would also add that while these fusion-based transition points are important for understanding what's going on in the interiors of these objects, they don't give us much information about how they form. So if we reframe our thinking a bit, we have our planets on one hand, which we know form from core accretion in a circumstellar disk, maybe gravitational instability, and then we have our stars, which are going to be that top-down approach, direct collapse, disk fragmentation. But the brown dwarfs don't have a preferential formation mechanism that will form just brown dwarfs. So it's probably a mixture of both of these things. In reality, what we're looking at is probably the tail ends of these two formation mechanisms overlapping in the brown dwarf regime. And what I would really like to try and understand is how does that overlap look? Where do we see the transition between planet-forming objects and star-forming objects? So this leads to a few big questions. Most fundamentally, we're asking, how big can a planet even be? What's the most massive object we can form from the planet formation mechanism? And on the other hand, how small can a star be? Can we even differentiate between these two formation mechanisms in the brown dwarf regime? And where my work comes in to try and address this is to ask what new insights we're getting from the transiting brown dwarf population. So you may ask why transiting brown dwarfs in the first place. And they offer a really interesting and new complementary parameter space to study these brown dwarf objects. Historically, brown dwarfs for previous decades have been studied from direct imaging in brown dwarfs in the field, where we understand them based on their spectra and their luminosities. Transiting brown dwarfs give us a completely complementary parameter space where we don't understand those, but we get dynamically measured masses and radii, which helps a lot to break this mass, radius, and age degeneracy that we see with brown dwarfs. And in the era of TESS specifically, we've finally reached over 50 transiting brown dwarfs discovered, over 2/3 of which come from TESS alone. And the work that that I'm going to show you here has increased this population by nearly 15%. So just to give you a bit of a flavor of the things that we're discovering, this is our most interesting new brown dwarf, TOI 5882. It's a 24 Jupiter mass brown dwarf on a circular 7-day orbit, but the host star has a lot of lithium in its atmosphere. And we don't necessarily think that this is due to youth. This host star is not a rapid rotator. There's no evidence of any nearby co-moving stars in the area. There's no H-alpha emission. There's no infrared excess. So we don't see any of the other signs that you would typically associate with youth. So maybe a more attractive explanation for this is that maybe this system underwent some sort of planetary engulfment, and that's the source of the lithium that we're seeing. If you're really interested in that, I would tell you to keep an eye out over the next few months for an upcoming paper by a graduate student at U of M, Brooke Cotton. But the rest of this talk is going to be much more focused on the population that we've put together. So this is where we stand now. This is all the transiting companions between 7 to 150 Jupiter masses. And you can see with the vertical black dashed lines, that's your traditional brown dwarf definition between 13 and 80. And now that we've put together this much more sizable population, we can start to look at the trends that are emerging. And maybe the most interesting and obvious one to point out so far is the lack of low mass transiting brown dwarfs compared to their more massive counterparts. So this deficit of low mass transiting brown dwarfs seems to coincide quite nicely with this random purple line that I haven't explained yet. So to dig into that a little more, this line's at 42 Jupiter masses, which, if you know anything about the transiting brown dwarf literature, is probably the most commonly cited location for this transition between planet and star-like brown dwarfs. And to understand where this comes from, we have to back up about a decade to this study of radial velocity companions that was done in 2014, where they noticed two key trends that they attribute to this transition. The first being that on short period orbits, less than 100 days, they notice a depletion of brown dwarfs from about 30 to 60 Jupiter masses. And then if you look at the eccentricity distribution, low mass brown dwarfs tend to have decreasing eccentricities as they get more massive, until right in the middle of that depleted region, 42 Jupiter masses, they claim, where the eccentricity spikes again and you see a much wider range. Now, these results have been cited for the decades since in transiting brown dwarf literature, often showing a plot very similar to this, where we take the transiting brown dwarf eccentricities now and notice an arguably similar trend that the low mass transiting brown dwarfs also seem to have lower eccentricities. But I would like to try and push back against this a little bit, because while at face value this does seem like a plausible conclusion, I would argue that the eccentricity is going to depend much more fundamentally on mass ratio instead of companion mass on these short period orbits that we care about for transiting systems. So if we remake this plot and adding in some low mass stars and some super Jupiters for good measure, the trend completely disappears. There's no more eccentricity dichotomy. So I think the transiting systems do not necessarily support a 42 Jupiter mass transition between planet formation and star formation, at least from the eccentricities alone. But hope isn't lost. Like we can look at more parameters than this, and this is a conference about understanding your host star. So one of the more interesting parameters we can look at is metallicity. And we've seen many times throughout this conference the giant planet metallicity correlation. So I won't dig too far into it, but we can use it as a bit of an inspiration to form a new hypothesis. So if your low mass transiting brown dwarfs are forming in the same way that giant planets do, you would expect that they would be around host stars that are metallicity enhanced. So if we compare low mass brown dwarf host stars to the high mass brown dwarf host stars, maybe we would see the same metallicity dichotomy. And if we try this at that same proposed 42 Jupiter mass transition, it doesn't look convincing. And in fact, if we use if we do a KS test, we definitely don't have evidence to support that these are two distinct populations. So maybe we can look at some other proposed locations for this transition, though. Maybe we should look at the hydrogen fusion and deuterium fusion boundaries. And again, it's not incredibly convincing. But I can stand here and show you histograms sliced up at every different mass all day. What we'd really like to do is try and systematically search for where this transition might occur. And as a very preliminary first attempt at this, we've done a sort of a suite of KS tests on the metallicity distribution for these objects, where we sort of slide around the boundary between our low mass and our high mass brown dwarfs. And we can see there's a minimum that pops out here. The way to sort of interpret this plot, if you're unfamiliar with KS tests, is that the lower the p-value, the more evidence you have that the two populations the two samples are coming from two distinct populations. So we can quickly just see what this distribution looks like if we chop it up at 66 Jupiter masses instead of 42. We're at the fusion boundary. And it looks a little more interesting. And just to flip back, this is a p-value of 0.048. And I think this is, if nothing else, a promising first start. There's a lot of underlying assumptions that are going into these metallicities. This is a completely heterogeneous sample, but as a first attempt, this looks promising. So I think metallicity could be a really powerful way to try and get at this question. Some of the next steps we really need to take are understanding the selection biases that are going into discovering these high mass systems, and also trying to curate a more homogeneous sample of metallicities for these host stars. But with that, I'll leave up some final thoughts and just say that I don't think the transiting population supports a 42 Jupiter mass transition, either in eccentricity or metallicity. But that metallicity does seem like a promising place to start in order to start answering some of these questions for transiting systems.
Questions? There we go.
Hi. So, cool work. The transiting brown dwarf population is obviously not representative of the entire brown dwarf population. They're obviously never isolated, and presumably by the bias of the transiting method, close to their companion. How well would you expect this to extend to the entire brown dwarf population? Could it extend, or would you expect maybe there to be different formation mechanisms?
Yeah, that's a really good question. I think there is definitely some extension that can be made. Like I said, this is like a completely complementary parameter space to examine, but you're right. I don't think it's outrageous at all to say that brown dwarfs definitely form in isolation. So I think those, it's fair to say that those objects are going to be dominated by a stellar-like formation mechanism. So I guess that's just to say I do expect them to be different distributions. I do expect that, and I would love to chat more, I guess, about how we might expect those to be different.
There was a question.
Very interesting result. I was wondering, maybe I missed this at the beginning, but what types of stars are you particularly looking at? Are you going all the way down to M dwarfs, or are you sticking with FGK?
Yeah, these go all the way down to M dwarfs. There are much fewer of them, but this is where the follow-up and discovery of these objects is largely it's largely an effort that's a byproduct of giant planet discovery. So it is essentially just all TOIs that are coming out of the test mission.
But
So
you're
we're
actually
not-
finding brown dwarfs around M dwarfs. That's awesome.
Thanks.
It's been proposed that transiting giant planets and transiting brown dwarfs are separated somewhere in the mass range of 4 to 10 Jupiter masses. Did you consider this mass range in your analyses?
Not this one, but that's very high on the priority list. The suite of systems that I have access to at the moment, at least for that I put together for this talk, only probes down to 7 Jupiter masses. But that is definitely the next step that we want to take, is to include a sample of essentially all giant planets and see how that changes the results. Yeah.
All right, I think that's it for questions.
Thanks, Paul.